Continuing our discussion of transformer protection, we'll now move along to look at a more complicated transformer connection. Now, this is one with a tertiary winding. That is, a Y-connected primary at 230 kV, a Y-connected secondary at 69 kV, and a delta-connected tertiary winding at 13.8 kV. The capacity of the respective windings are 65 MVA for the primary, 40 MVA for the secondary, and 25 MVA for the tertiary. The Y-connected windings in both the primary and in the secondary are grounded through their respective neutrals. Note that each external line connection is provided with its own set of CTs. This is important, as we shall see. Also, in each phase differential relay, a separate restraint coil is available for each CT connection. As we discussed in the last segment, the CTs in the Y-connected windings must be connected in delta to avoid operation on external ground faults. And as before, in order to accommodate the 30-degree phase shift, the CTs in the delta-connected tertiary must be connected in Y. Here is the three-line diagram. To determine CT and relay connections, we must carry out a phasing study. When dealing with multiple winding transformers, it's always advisable to study CT phasing in pairs of windings, considering the third winding to be at zero load. Let's start with the primary and tertiary windings. Line current IA passes through the A phase transformer primary and into the neutral. This gives us current IA this way in the CT secondary. Similarly, IB and IC pass through their respective transformer primaries and into the neutral, giving IB and IC in the CT secondaries. The resulting secondary relay current, shown by a yellow arrow, is IA minus IC. Similarly, the other secondary relay currents are IB minus IA, this green arrow, and IC minus IB, this blue arrow. Now let's look at the current flow in the tertiary CTs. The current in each phase of the tertiary winding corresponds to its primary, IA, IB, and IC. However, as the transformer is connected in delta, the line currents will be different. For example, in line A, the current this way is IA minus IC, shown by a yellow arrow. Here we have IB minus IA, the green arrow, and in this line, IC minus IB, the blue arrow. The CT secondary currents are representative of the line currents and are indicated by appropriate yellow, green, and blue arrows. These currents from the tertiary transformers are the currents leaving the relay. Having established the direction of the currents for clarity, we'll remove polarity marks. Now let's look at the current flow in the restraint coils. The secondary current IA minus IC, the yellow arrow, enters this differential relay phase A. The current leaving this phase A restraint winding is also IA minus IC. Remember, the current in the other restraint coil is zero. Therefore, the current passing through the relay operating coil must be zero. This is correct. The differential relays B and C have similar currents, and the current in their operating coils is also zero. Now, having checked the primary and tertiary windings, let's check the phasing of the CTs in the transformer secondary. These are delta connected like the primary, hence, like the primary, the currents from the relay are IA minus IC, IB minus IA, and IC minus IB. With balanced operating conditions, these three sets of currents cancel, and no current will flow through the operating coil. If an internal fault occurs inside the transformer, then out-of-balance currents flow in the operating coils and the relay will trip. With the multi-winding transformer, selecting the correct CT taps and calculating the mismatch is similar to our earlier example. The essential feature is to work with one pair of windings at a time and assume the same MVA for both windings. For example, let's consider 40 MVA passing from the primary to the secondary. The line current in the primary will be 40,000 divided by root 3 times 230, which equals 100.4 amps. Assuming a CT ratio of 30:1, and remembering that the CTs are delta connected, the secondary current equals 5.8 amps. On the secondary side, the current in the transformer windings will be 40,000 divided by root 3 times 69, or 334.7 amps. Assuming a CT ratio of 400:5, that is 80:1, and remembering the delta connection, the CT secondary current will be 7.25 amperes going to the relay. The ratio then between IH and IL equals 5.8 divided by 7.25, or 0.8. Now, let's suppose that our taps are set on 5 and 6 respectively, giving us a tap ratio of 0.83. Our mismatch can now be calculated as 0.83 minus 0.8 divided by 0.8, which equals 3.75%. This is well within the transformer differential relay restraint setting. A similar calculation would now be made for the tertiary, using 25 MVA as the base. At times, the mismatch may be too high for good reliability, even when using the whole range of taps. In this case, it may be necessary to use auxiliary CTs in the main CT secondary circuit. In this single line diagram, you can recognize the connections to one phase of the differential relay. However, in following through the operation, it helps if we connect the other end of each CT, first for the two outer windings. If we consider the load on the third winding to be 0, we can see that there is balance here. The same secondary current passes around this circuit with no flow through the operating coil. We must remember, however, that this is a schematic, and with the CTs connected in delta, CT secondary current is not the same as relay current. CT secondary current times the square root of 3 equals relay current. Now, if there is load in the third winding, we must connect the third CT like this. Suppose we have, say, 0.6 amps in this first circuit, 0.5 in the second, and 0.1 in the tertiary. The current will flow like this, and as we can see, it still balances, and there is no flow of current through the operating coil. In studying these diagrams, usually these additional connections are left out for simplicity, but they are understood. How would we handle this transformer differential protection if the differential relay had only 2 restraint coils per phase, like this? In this case, we would have to parallel the CT from the third winding with that of the second. As long as the load in and out on all 3 windings balanced, this would be acceptable. But supposing we had to operate this transformer with the high voltage primary breaker open. In other words, the power supply into the transformer would now be from this 69 kV side to feed the outgoing 13.8 kV. If the secondary currents were perfectly balanced, there would be no problem. But as we know, there is always some error current, and this would pass through one restraint coil and then through the operating coil. In fact, now we have only one restraint instead of the previous 3. This would probably be insufficient, especially for a heavy through fault on the transformer. Hence, the reliability of the protection would be considerably reduced. For this reason, remember, CTs should not be connected in parallel, and each CT should be connected to a separate restraint coil. Here's another example of multiple connections to transformers. This single line diagram shows that the primary can be fed from 2 different sources through separate breakers. Similarly, the secondary can be fed to 2 different loads through separate breakers. In other words, there are 4 connections. We must have 4 CTs, and these will be connected to 4 separate restraint coils on the differential relay. By now, it must be clear to all of us that differential protection on transformers is not just a matter of installing a differential relay. The connection of CTs requires careful study, and remember, there are many different applications. Each installation must be studied on its own merit. You should try to obtain differential protection circuit diagrams for your own power system, and study these with the help of your supervisor. At this point, let's take a break, and then we'll come back and continue our study of transformer protection. For now, please switch off the tape and review this material in your workbook.